Buongiorno a tutti, buongiorno e bentrovati. Siamo al primo webinar della giornata. Mi farà compagnia oggi il mio collega Giorgio Di Lorenzo, responsabile commerciale di Rete Informatica Lavoro. Ciao Giorgio, benvenuto. Benvenuti quindi all'intervento live dedicato all'azienda Arηs, un gruppo di società IT completamente indipendente, il cui headquarter è in Lussemburgo, ma è attivo in Belgio, Francia, Grecia, Portogallo e Italia. Il gruppo è specializzato nella gestione di progetti e sistemi IT complessi. L'azienda è impegnata nella ricerca di candidati IT con un fondamentale requisito, la conoscenza fluente dell'inglese. E in inglese è stato programmato anche il nostro webinar. Lascio la parola a te Giorgio per presentarlo. Ciao a tutti.
Okay, good morning. It is with great pleasure that we welcome Thiemo from Arc's Group, our first guest of the morning Architecture-Day. With him, we will explore the microservices architecture through the webinar, How to Handle Distributed Transactions in a Modern Microservice Architecture. Thiemo, I would ask you to introduce yourself and tell us about Arc's Group, which is a very interesting IT European company. We invite the audience to visit the virtual office for more detailed information. And Thiemo, for any need, we are online at your disposition. So see you in 45 minutes to answer the audience questions that please must be written in English in the chat box.
Okay.
Okay.
So I'll take over then. Yeah, fine. Let me see. Okay, whoa, that was too fast. So, good morning, everyone. My name is Thiemo Morth. I'm working as an IT architect in the Arc's Group. So, therefore, you can expect a presentation about software architecture today. But let me first tell you a bit about the group. So the Arc's is the Arc's Group is like meanwhile a real diverse group. So we are, let's say, split in multiple entities. So each of those entities is more or less independent, but we still belong to the same group, and we still are, let's say, supporting each other a lot. So, for example, I can give you a good example there. So I'm at the Arc's development entity, while I'm at the moment working in a project for Arc's Bike Seat. So, so there is a lot of possibilities. So we have still a lot of. Video zu starten. Hello, can you see me again? There was an alert from the meeting platform.
Yes, we see you.
Okay, great. So what was I saying? Yes, so most of the project which we are doing are consulting projects, so which mean you can, let's say, contact Arc's and ask for a software you would like to have developed, and we are going to develop it for the customer. But there is a lot of maintenance as well, operation. Meanwhile, we are extending in the area of cloud development a lot. So we have a lot of cloud development projects at the same time as we are also doing cloud operation projects. So while the project is already live, that we do the monitoring and all the operation, everything which is needed for that. But meanwhile, we also start to develop our own products. For example, there's Fleetback, which is a software as a service, which is developed by Arc's and which is offered from Arc's to car dealers. So it's doing all this after sales, which it supports with video chats and pictures, which you can share with mobile on the mobile devices. So there is a huge range of different things you can do in Arc's, and that's also the goal of the company, to diversify the, let's say, the projects, the products we have. And the good thing is, like, I'm meanwhile for 6 years as Arc's. I started as a senior developer there. Now the last 3 years I'm working as a software architect. You have the possibility to, let's say, switch projects. So which means after a few months, a few years, depending on the project, okay, you can just go into the next one and you see something completely new. So that's, for me, one of the biggest advantage is that it's never boring, because you have to learn all, let's say, few months, few years, a new project, a new customer, a new technology. So for me, it's really interesting to work at Arηs. Okay, that's enough for the advertisement. So I go on with the presentation. One thing, this is a presentation which was meant for a software developer conference. So I tried to simplify it a bit, and because I've seen that the audience, so the participants, that they have really different backgrounds. So first I will give you a few backgrounds, so that's the settle the ground part, so that you at least understand some basic information, because you need that first to understand the problem which I'm going to introduce, and also to see what possible solutions can we have for this problem. Here's some credits. So there is a blog post. I put the link here so you can check it out if you want, from Bilgin Ibrahim. I hope I spelled it correctly, from Red Hat. So basically the presentation is at least parts based on his blog post. He did a really nice summary of all those possible solutions. So therefore I took some information from him. There's one thing. Sorry, I'm suffering a bit from a cold. I hope that my voice won't break. If there is something that you don't understand during my talk, just immediately write the question into the chat. So because I don't want to lose anyone during the talk. But if you have some, let's say, advanced questions, just keep them in mind, and you can ask those in the question and answer session after the talk. Okay, so I'm going to start. Why is this not working? So the first basic information or knowledge I am going to introduce are transactions, or more precisely local transactions. Here on the left side, you see like a typical simplified view of an IT system. You see the gray box, which is one common runtime. So it could be a server. And inside you have typically, let's say in a traditional way, the application is layered. Like you have a user interface which accepts some requests from a client. Then from the user interface, it goes through the business logic. Finally, you have a layer which is responsible for handling the access to a data source. In this case, here is a relational database as data source chosen, but that's like a general structure. Okay. Now, why do we need transactions? In a relational data source, typically the data is organized in normalized tables and relations between the data in the tables. So just imagine table A could be a list of addresses, for example, while table B could be a list of customers. So, and each of the column is some piece of information of the address, like the street or the house number, the zip code, or things like that. And the same for a customer. So, and typically, if, let's say, the client sends a request to the application, the business logic spans more than just one object in the database. So, which means, for example, you have to insert here a new row into this table because you want to insert a new address, for example. Then you want to put a relation from your customer to that address because you want to say, okay, that's one address of my customer. So you define a so-called foreign key because it goes from one table to another table, from this row in this table to this. And for example, you could set a flag which marks this address as the new default address to be used. So that's actually, you see, this one operation are three operations. So the one business operation is three operations. So, and the purpose of a transaction is to handle those things as one atomic operation. So you see here's again the three things I told you, like insert a row, update the foreign key, that's this relation here, and update the column to mark this one as the new default address, for example. And the idea is that you need to bring the system, so with the system, in this case, the database state, from one consistent state into another consistent state. But meanwhile, it might be inconsistent. For example, if you just insert this row, and then it fails, okay, you have something like a zombie address, which means an address which does not belong to anything. So therefore, you see, typically it's like that. You first say, okay, I want to start my transaction. Then you do all the simple operations which are required. And at the end, when you think you're done, you commit those transactions. And only if the commit succeeds, those changes are effective. So if, okay, I will tell you that later. If, for example, the step number 3 would fail, you could roll back everything. So which means one characteristic of a transaction is atomicity. So which means either do everything or do nothing. So that's the first. There's this called ACID principles, which apply to a lot of data sources, especially to relational databases. Every letter stands for one of the, let's say, capability. The A is the atomicity. I just told you that. So you want everything which happens inside one transaction as an atomic operation, either all or nothing. The next one is the C, which means consistency. So which means you bring the system from one consistent state into another consistent state, and any intermediate state is invisible. So the I is the isolation. That's what I meant with invisible. So it means, okay, you start a transaction, you begin changing things, but unless you commit these things, it's not visible to anyone else. You know, typically, let's say a software is concurrently. So there's multiple processes running in parallel and reading and writing data. So it means like, while the transaction is not committed, everything you changed in the database is not visible to any other process who is going to read data from the database. Just after you do the commit, it's visible for everyone. So that's the isolation level. There is multiple isolation levels, but I skip this for now. And the last D is just the reliability, so which means the data is stored in a persistent way. So even if you would restart the database server, the data is still there. Okay. That's for local transactions. We have to understand local transaction because that's basic for distributed transactions. Okay, so next thing to know, here, it's about a monolith application. Why is it going off? Sorry, I don't know why the camera is turned off. It seems to do this automatically. Okay. So a traditional way of software, let's say a few years ago, and you see it still, is like a monolith application, which means everything is deployed together in one runtime, like I showed you already on the first slide. Nowadays, we are going to develop a lot of things as microservice, not everything, but a lot of things. So therefore, I'm going to introduce you very briefly to the concept of microservices and why do you need that. While the monolith application looks from the outside like that, if you do it, let's say, a bit like a detailed look, you see that the actual application consists of multiple modules, so inside. So the modules are responsible for doing different things. Here you see I tried to highlight module A, module B, and module C. All of those modules can implement some aspects from those layers, like the user interface, the business logic, the data access, but they don't need to do that. All of them here you see still have one database connection and saving everything in the same relational database. Okay, but actually there's a problem with that, and therefore we want to go into something like that, which looks more like a microservice architecture. So what did we do? So basically we tried to vertically split those modules so that we have independent modules. You see here you have like module A, module B, module C. One thing which is very important here is you see this gray box, which is the runtime. So the server in which this is deployed. So you can think of a server of that. You see here we have one runtime for module A, a different runtime for module B, and a different runtime for module C. So why do we do that? What's the purpose of splitting all those things into multiple things? One of the, let's say, one of the most important things is about scalability, and the other aspects are about use the right tool for the right thing and about organization. So typically what should happen? So just keep in mind what I said. Imagine that the whole application consists of those 3 modules, yeah? But now you have 3 different teams who are going to develop that. So which means you have one team responsible for module A, another team for module B, and another team for module C. So first of all, you ensure that you don't have any unwanted calls, communication between the modules. So it should go to a well-defined API, and it has to go to a well-defined API because you are crossing the borders of the process. So this is another process of this. So you cannot just by accident call from the UI of module A, for example, something in the database access layer of module B. And those things can evolve independently, which means you could have 3 releases of module B while you don't touch module A, for example, unless you can keep the as long as you keep the interface stable and still compatible. So those can have a complete different life cycle, each of those modules. So this allows, for example, that team number B is much faster of adding new features, and they are not depending on team number A, which must also release their products just because B want to add the new feature. So that's the organization aspect. Another aspect is about, I mentioned that already, use the right tool for the right purpose. So since you're not living in the same runtime anymore, you can use completely different programming languages, for example. Imagine this could be a Java application, maybe a Java enterprise server, something like that, a traditional thing going to the database. While this is something, you see, I even did a connection to a different type of database. Here it's like a NoSQL database, like a document database, which is used by this one, because it might be better for the use case that B is doing. So for the processing that B is lodging, that they store their data in a document database instead of a relational database. And okay, if they are doing so, they might decide that because the logic is changing quite often, they might prefer to program all of this as a Python code instead of Java code. That's possible. If it's better suitable for the use case of module B, use the right tool. So use more script-based language like Python or JavaScript, for example, is also another thing. Use the right backing services to store your data. And you see module C, for example, is very simple. It does not have any UI, it does not have any database layer, so no persistent data. It might be that module C is just a, let's say, a CPU-intensive background processing which have to be done. So that's the right tool for the right purpose thing. But the other point is scalability. So you want to be able to handle those things differently. So therefore, I go to the next slide and I tell you something about scaling. So typically, why do you want to scale? Because the load to your application increases. You start small, yet you have like just a few users, and your application is that famous suddenly that you get thousands of users, and you have to be prepared to handle all the requests, which are way more than initially. So one dimension of scaling is so-called vertical scaling, so that you see here on the left side. What does it mean? It means, okay, you have a small server beginningly, and then you get more requests, so you need more resources. But just take a bigger server. You see, it doubles the CPUs and doubles the main memory, for example, and you can even go to an even bigger one. The thing is, this has limitations. You cannot just add more hardware. At some point, you just have some physical limitations. But also, if you see here, it's like cost limitations, because this gets really expensive at one point. So the better way to scale is to use horizontal scaling. So instead of using a bigger machine, you just use 2 small machines or 4 small machines. So in this case, you can add as many, let's say, new nodes as you want if you get more load. So that's way better to scale like that. And it's also cheaper, by the way. For sure, if you want to do that, you need to foresee horizontal scaling in the architecture of your application. What fits very good is to use stateless services, because in the end, if a request which is coming from a client, and it doesn't matter which one of the machine process it, then it's easy to implement. But if there is some state maintained, which means some kind of session information, for example, so between two subsequent requests, so then because the machine need to know, okay, what happened in the first request for processing the second request, then it's difficult to implement this kind of horizontal scaling, because you would need to implement something like sticky sessions, like a routing mechanism, which always routes the client to the same node, and that's complicated to do. So, well, this for now still has nothing to do with microservices. It's just two different ways of scaling, either vertical or horizontal. But just to go back, if you remind this, now we splitted our application into multiple runtimes. So they have, all of them has a gray box. So, and now decide, for example, this C is really CPU intensive. So we need a lot of nodes horizontal next to each other to do that. We get actually a third dimension of scaling, which I would call the functional scaling, because now we have divided the complete application into microservices, which can be scaled independently of each other, because they are different processes. So, for example, you see the UI here, Web 1, Web 2. It's enough to have 2 instances running to handle the load. But just imagine this worker, where you see 4 instances of the worker, could be module C, which just do some CPU-intensive processing. So from this, you can have 4 instances. And if the load increased, you just on demand add another one without impacting the other stuff. So that's the biggest advantage of microservice, because you can scale each service independently up and down, which means also if you don't have that load anymore, it can just destroy 2 of those instances and just keep the 2. That's possible to do this automatically. Okay, so that's what I want to tell you about microservices. One thing I forgot, it's also about failure isolation. Just go back. You see, for example, if there is a failure in this module, it could be that part of the of the application doesn't work anymore because this module is failing. But still, let's say the main part of the application is still functional because those modules are fine. While if you have this, if here C fails, everything fails and the complete application is down. Okay. So that was a lot of advantages I told about microservices. But unfortunately, there's not just advantages. There's also some costs or some trade-off you have to take into account if you are using microservice in the microservice architecture. And that's the problem I'm going to talk today about. That's the so-called dual write problem. So let me just explain you the problem because it's important that you understand it. Just suppose we have 2 microservices, service A and service B. And the use case is really simple. So the client calls some, let's say, some operation which changes the state of the application. So it's a write operation. Yeah? It changes something. It doesn't matter what. And then first thing, it has to update its own database. But because it also impacts the state of the other service, it has to call the second service. The second service has also to update something in his database. Okay. And what you see here with the dashed line is the so-called expected transaction boundary. So which means, you remember I was talking about local transactions and it should be an atomic operation. So which means this is the atomic operation, so which is into this transaction boundary. So which means if this succeeds, but this fails, okay, this need to be reverted. So either all or nothing, and the same is the other way around. So either both writes are done to the database or none is done. So that's what we want. But the problem is we cannot do this in a local transaction anymore because you remember the gray boxes, which are the runtimes. those is two different processes, and a local transaction cannot span multiple processes, so it can just live within one process. So and that's the problem which you get if you decide to go with a microservice architecture. And in the rest of the talk, I'm trying to introduce you some possible solutions to handle this. Okay. Here it's like a short preview. There will be at least four solutions I'm going to show you. And you see, at the end, we will do an assessment of those solutions. And the criteria to assess them are on the left side of the diagram is the scalability. You see, some of them are way better scalable than others. So they are better in handling more load coming to the application. And the other dimension is the consistency. Sorry. So what does it mean? Here on the very left side, you see so-called immediate consistency. On the right side, you see eventual consistency. I have to explain you that. It just means, like, if we go back here, just suppose this would be possible, which you see here, which is not the case. Immediately consistent means the client does one business operation, so one request, and when the request finishes and returns to the client with a response, the data is persistent immediately. So which means it has been persisted to this database and this database. Yeah? So which means the client can be sure that when he gets the response to his request, that the data is persisted immediately. So while the other techniques, they switch from immediate consistency to eventual consistency. So that means the client receives his answer, but the data, not all the data is already saved. It could take a short amount of time until the system is in a consistent state again. So this is, let's say, not like hours. Typically, this is, let's say, like seconds or even milliseconds. But it's not immediately anymore, since something is done asynchronously later on. So that's eventual consistency. So we can guarantee that the data is consistent, but not now, but eventually, so a bit in the future. Okay. So the first solution which we have for the problem, which using microservices, and how can we solve the dual write problem? So how can we write to do databases? It's quite obvious it's not to do microservices. Okay, it might sound a bit silly, but if you have an application which have really strong consistency requirements, so that's very important that you know your requirements. That's the first thing you have to do. But if you identify that you have really, let's see, some services, let's say, assume you have 5 microservices, that's not much, it's just a few. But if you have the requirement that 2 of those microservices have a really, really strong requirements regarding consistency, then maybe you can decide to try to use as much as possible of the best practices which have been introduced by microservices, but don't do real microservice. And that's what we call a so-called modular monolith. So in contrast to a monolith which has been grown over years, and there could be something like an unwanted dependency inside that, that's a small modular monolith which you create on purpose, and you try to apply as much as possible of the best practices for microservice. So what does it mean? You see, here is something which I called lib A and lib B. So it's library A and library B, but actually those is the implementation of service A, which you've seen in the previous picture, and service B. So we are trying to develop them independently by independent teams as libraries and still put them together in the same runtime. Putting them together in the same runtime, I think you can use, for example, Wildfly server for that. He's able to join modules dynamically. You need a bit of, let's say, some kind of shell service which gets the request, then first calls A and then calls library B. But that's possible. And then the good thing of that is that you have basically just one connection to the database. So you have one runtime, one database connection, while logically it's two different things, but physically it's one connection. So that means you can handle, let's say, service A can update his tables, and while service B updates his tables in the same local transaction. So if it fails something, say A succeeds, B fails, we get an error, we can simply roll back the complete transaction in a generic way, and all the changes have been rolled back. So no trace that something has changed. So while in the code base, you can do the split by developing this as dedicated modules, you can also try to logically separate the data in the database. So for example, you can create a schema. A schema is a collection or a group of tables. Depending on the database vendor, it sometimes has even a different user if you want to do that. But which means you can try to avoid that let's say, anything from service B is accessing anything in schema A. So there is a bit of organization. But it's possible. So the first solution is decide on purpose for only those subsets, so those two services, not to do them as dedicated microservices, but do them as a modular monolith. So that's sometimes one of the simple solutions. Here, that's what I mentioned before. Applying the best practice we introduced for microservices to actually non-microservices. Here you see how you can isolate the application code. So, and here's like from left to right, the further right you go, the more isolation you have. And here in the second view is the same for the data. So what you can do, you can separate your classes when you write your application code in separate packages. Okay. But they will be still in the same project and in the same module. Okay. But okay, the next step would be one code base, but you would decide to have different build modules. So which means if you want, you first build library A and library B, and then you can join them together, but they are still in the same source code repository next to each other as two sub-modules of the same project. Separate source code repos. So you can even go further. So which means you create one Git repository for library A and one Git repository for library B. So dedicated teams, so one team A, team B can develop their library. For sure, there's limitations. So for example, they have to use the same programming language because they are deployed in the same runtime. And there is some collaboration needed between the teams because you need to ensure that the interface still matches. So therefore, it's not that flexible as microservices, but it applies some of the principles. So try to isolate as much as possible. And as soon as you want really dedicated runtimes that you see here, like not in the same gray box, then you have a real microservice. And the data, I told you that already, you can just use separate tables for data. Then you can group the tables together in schema. So it's like logically grouping databases. But as soon as you start to use dedicated databases or dedicated database servers, then you cannot have, let's say, a local transaction which spans all of that, and it's a microservice. So that's the simple solution, not to do microservice, but on purpose for a limited set. Okay, let's go on with another possible solution. So now, here is the use case of so-called distributed two-phase commit protocol. What does it mean? I have modified the example just a bit. What you see here is like service A has to write something to his database, and then he has also to write a message into a message broker, into a queue, which is run from a message broker. So you see the transaction boundary here. So we have to commit. We have to do this action and this action at the same time. So forget about the blue thing for now. There is a protocol, a standard protocol, which is two-phase commit protocol, which you could use for this use case. It is implemented by some data sources, so by most of the relational databases, for example, by the ActiveMQ ActiveMQ message broker, but you're a bit limited with that thing. I have to speed up a bit. So here you see how it works. So it's called two-phase commit. Why? Because you need to have somewhere like a central transaction coordinator. This transaction coordinator first asks the first data source, so that could be this database, please prepare the update. And then it asks the second data source, which could be this queue in the message broker, please prepare the update. Okay, and everything, if all the involved data sources say, okay, I'm prepared, then it says now commit and now commit. So in this case, or at least in the successful case, you can be sure that finally the data is committed. The thing is, this thing is a bit not really scalable. First of all, you have a central transaction coordinator that need to be a singleton instance, so only one instance of that, who is the one who's responsible. So which means every two-phase commit depends on the transaction coordinator. So that's one limitation for the scalability. And the other thing is like those things are happening synchronously. So which means the two-phase commit calls, let's say in a synchronous call A and waits until it returns, and it calls B until it returns, and then it does the same for the second phase. So while this is ongoing, everything waits until the transaction finish. So you block a lot of resources. So you can use that. You have a limit. You can use it as a standard protocol. You just use a different. You just configure it, and it works out of the box. But you're limited to only a few vendors, products, and you're also limited in terms of scalability. So the next best thing you could do is a so-called orchestration pattern. So what's that? Basically, you have you still have a central orchestrator, and it looks a bit like that. Sorry for my voice. So either you have a dedicated orchestrator, like in the picture on the right here, or you just depict one of your services as the orchestrator. That's another option. So basically, the client, let's say, starts one of those business operation at the orchestrator, and the orchestrator is the one responsible to bring the system in the expected state. So it would first call service A, wait until this is done, then service B until it's done, and like that. The thing is, you see here, the transaction boundary is just inside this, because the orchestrator needs to know the state of the overall system. So it has also to save the state of the overall business transaction, which is started here. But then let's say, just do the first step, do the first invocation of service B here, and then it writes into his database, okay, service A called, so invoked already. So it has to record the state of the overall transaction, but it can do this in his, let's say, with a local transaction in his database. The problem is now, the protocol doesn't matter here, by the way. The write can be a synchronous call, like calling an HTTP web service. It could also be, let's say, sending a message in an event queue. So it's the same thing. The protocol is really, completely unrelated to the protocol. The thing is, okay, just imagine that service A, B, and C managed to do his stop, but at some points service D fails. In this case, the orchestrator has the responsibility to call compensation actions, which means revoking things that has been applied before. Just imagine you have like a more complicated flow like that. Here in the middle, you see an example for the orchestrated business flow. Like first you get an order, then you need to check the inventory, then you need to check the payment, and then you do have to execute the payment, finally do the delivery, something like that. So while the state of the overall system is recorded in the orchestrator, it calls at some specific points microservice. Here's the inventory check, here's the payment service, the delivery service, which are executing the dedicated steps. But just imagine the delivery failed. In this case, there need to be a compensation action at the payment service, for example, to revoke the payment, so to send the money back if it's already been deducted from the account of the customer. So that's one option. I try to finish fast, sorry. Another option, it's even more flexible, but it has also some drawbacks. That's the so-called choreography pattern. In this case, you don't have any central point that knows what is your carrier path. Okay, later. This question about the carrier path I will answer later. Okay. So here you don't have any central point. So everything is event-driven here. So which means the client gets a request, it updates its database and just send an event to the event store. Says, for example, order created. Yeah. So it could be service A. It does not know who are the ones who are depending on that event. So, but service B is listening for those events as well. And at some point says, okay, I'm interested for order events. So it starts acting. So in the end, what is going to happen is like, instead of having a central point of coordination, you have like a decentralized flow of events. So that could be like a cascade of events. At some point, service A does not know that also service D is involved in that. So it is really flexible and fast. It's highly scalable, but it has a drawback in terms of error analysis, because you don't have a central point that know what is the state of the overall transaction. If there's a failure, you have to check what happened in service A. Okay, it sent an event. What happened in service B? So it's really fast, but it is also hard to analyze in case of issues for this thing. One thing which I didn't tell you, that there's actually that there is also a dual write problem inside this flow. So like a dual write problem inside a higher order dual write problem, because I told you you have to write to the database and write the event. So it's a dual write for that already. There's different strategies you can do. For example, the local commit, then publish. I just skipped the other one because I'm running out of time, which means you save to the database, and when this is committed, you publish the event. In this case, it could still be that there is a small portion of time when this local transaction has already been committed, but let's say the sending of the event fails. In this case, okay, what you can do, if you are lucky and you have the control over your service and all subsequent services, so upstream services, you can make things idempotent, which means if you invoke the same operation more than once, multiple times, the result is always the same. In this case, you can just do a retry because, okay, sending the message failed, okay, you just retry the whole thing again, while this has already been committed, let's say, so this commit must be idempotent, so just doing the same thing again must lead to the same result, and you send the message. It could also happen that you have duplicate messages, so duplicate events. In this case, that's what I said, all upstream services need to be implemented in an idempotent way as well. Okay, I have to hurry, so I skip this one. There is another technique which you could do, which is just instead of using a database, you do event sourcing. What does event sourcing mean? It means like instead of storing the state of an object, you store just the changes of an object. So it's like a list of changes. And if you want to know the current state of an event, of an object, you have to just go through this list, apply all the changing events to compute the actual state of an object. For example, the good thing is, like in this case, you could write here, it writes an event to the event store. So there is no need to update another DB because the data source is used as a communication layer as well, which means you don't have this dual write problem, which I just mentioned before. You could just write the change event and you can just, service B can listen for events. So here's one local transaction to write a change to an object. This one will get notified and he does something because of this change. The drawback is, I saw that it's event sourcing. If service A want to know the actual state of an object, like a user whose name has been changed and his salary has been adapted, for example. In this case, you need to read all the events, apply them to know what is the actual state of my user. So it's the user with the new name and the user with the new salary, for example. Okay, I know I was running a bit out of time. So therefore, just I want to do a short comparison of those solutions. So with a modular monolith, you have immediate consistency, but it's not really scaling that well. The next better thing you could do is using two-phase commit. You can decouple the service to some extent, but because you have a central coordinator, you have synchronous invocation of the XA data sources, so the resources participating in the two-phase commit, it's also not that scalable. The next thing is orchestration. Here we enter the phase of really eventual consistency, because at some point the orchestrator drives the system in a consistent state, but it could be a bit later. Still, you have a central element, which is the, let's say, the orchestrator itself. So therefore, you have some limitations regarding the scalability, but you have also the advantage that you have the state of the overall transaction at one place. Choreography is even more scalable, since you just kick off one event, which could trigger in a cascade a lot of other events. And it's also easy to extend. If you have a new service, which is, let's say, listening on a specific event, you just edit. You don't have to change a central orchestrator. But it could be sometimes hard to know what is the state of the overall system, because you have to check each of those components one by one if you want to do an analysis what happened in case of a specific error. Whoa. That was a bit fast at the end. So, because I ran out of a bit of time, but I hope that you learned still something new.
Okay, very well. Thank you, Thiemo. Very interesting topic. Someone asked if it would be possible to review this talk. Well, all the Tech Jobs Day talk can be reviewed in the next few days in the Rete Informatica Lavoro YouTube channel. I think that you have some question. Can you see in the chat?
Yeah, I see the question. So I don't see any question regarding to the topic. So either it was very clear or it was too complicated. But there is topics regarding the carrier path at Arηs, and okay, what I would like to what I should suggest how to work in the company like Arηs. Okay, the carrier path. Well, there is carrier. Really, we have definitions of carrier passes. So it depends of what you would like to do. For example, you can start the business analyst part. So at some point you have, let's say, the developer path. So there, from a developer, if you just come from the university, for example, you start as a junior developer. At some point you get a media profile. I think it's just called developer analysis developer. I'm not sure about the complete name, but anyway, it's a media profile. At some point you will become a senior developer, and you have here you have another choice again. You can always switch between career paths. For me, it was, let's say, I was working like for 2 or 3 years as a senior developer in Arηs, and then I switched to an architect. While architect means I'm not doing these nice drawings, which I just showed you. I try to also keep a bit, at least, in my role as a developer, because developing is what I like, for example. So it's not like strictly separated that you say, now you're an architect, you're just there to define nice pictures and review the architecture. So I say, I want to feel the pain myself sometimes, because, you know, sometimes you have a great idea how you could implement something and you start implementing it, and it turns out that it's really complicated to implement things. If you're still, let's say, with one foot as part of the development team, you can understand this way better, and I think you can also propose better architectures afterwards. So that we don't have a strict separation. It's like you are still allowed to do things that you like. For sure, you have to do the things that are, let's say, that correspond to the role that you take as well. Another part, so you have the developer, which you could go as an architect, or I think even senior architect, and I'm not sure. And then there you could also at some point say, no, I like, let's say, leading people. So you could go in the direction of a team leader. So typically as a team leader, you still need some kind of technical background, some programming background to understand, okay, what you should lead there. So in this case, you will get more management responsibility for the team, but maybe less, let's say, the things you do as an architect. So you could, from the team lead position, you could evolve into a delivery manager if you want that. So then you are completely outside of, let's say, technical tasks. So you are responsible for contractual things with the customers. You have to check about the scope you have to deliver at which point. For sure, you need still to understand the application and talk with the tech team. But the further you evolve into, I think there is even a next step in project director if you want to become that. But the further you evolve in that, the less technical task you will have, for sure. There is specific topics for the cloud area. We created a lot of cloud positions now. So there you also have developer, DevOps, cloud architect. We have the same like without cloud. There is some predefined paths, but I would recommend you to ask this question to the HR people. So you can join the virtual job with them, and they know way better than me, honestly. I just know the ones which are responsible for me, and for the others, I don't know the details that much.
Okay. Well, Thiemo, it's been a pleasure having you here today with us, and we hope to have you with us also the next edition of the Tech Job Day, and I wish you all the best. Thank you again. And have a nice day.
You too. Bye-bye.
Thank you.